Hello, my name is Skunbut, and today I'm in the probability and statistics for this class in lecture 4 for more counting principles. So last week we learned about the basic counting principles. So we have the rule of, I don't have it here. We have learned about the rule of product, the most basic and the most useful one. And then we also have the rule of sum. Say that sometimes you can split things into two groups and count each group one at a time. And we learned about the two basic functions called the permutation and combination. So that's from last week. So in this week we are gonna expand on that to see if we can solve other types of problems using these four basic principles. So first of all, we have what we call the restriction or requirement or conditions, some kind of extra requirement that you need in your counting. So in the real world problem, sorry about text, we can use the I have it here: rule of sum, rule of product, permutation, and combination. So they serve as the building blocks for the basic counting principles, but they are too simple. In the sense that we assume that everything is different and everything is easy to count. But in the real world, we have some extra requirements or extra conditions imposed on the problem. For example, we may ask how many lottery tickets are there that has no 8. If you count how many lottery tickets are there, let's say it's Thai one where you have 6 digits. So the number is 10,000. Oh, I mean a million. And then if you ask how many of those, among those million tickets, how many are there? How many of them has no 8? Then use a different technique. Or you can ask how many ways you can form a team of 5 arrangers, such that two members have the same class. Or 2 members have the same class, or something like that. Or, if you are in college, which I think you are, we all are, including myself. If you schedule 6 courses a week, and you want math and history to be on the same date, for whatever reason, then how many ways you can rearrange those 6 courses? The point is that there is no definite answer to these questions, right? And unlike the first 4 things on the top, right? All the types of problem require analysis. you have to have seen enough number of problems to be able to know how to tackle a new problem. And so it's all about experience. So let's see if we can use some commonly used technique in these kind of problems. For example, so in the first example, we are asking how many permutations are there of 5 people, such that Tom and Jerry are adjacent to each other. And so here, if the question stops here, if you just ask how many permutations are there of 5 people, the answer is simply we have 5 and then we permute 5 of them, and with 5 factorial over 5 and that's 5 factorial. That's the formula from last time, which is 5 factorial or exactly 120 ways. Then the question doesn't ask for all permutations. The question asks for those the number of permutations such that Tom and Jerry are adjacent. So for example, you can have, let's say those 5 people are A, B, C, Tom and Jerry. A, B, C, T, J. But you can of course you can arrange them in this way. You can permute them in a line this way, A, B, C, T, and J. But and this is what we want, right? We want Tom and Jerry to be adjacent. But if you switch things a little bit, for example, you have A and then T and then B and J and then C. Then this is a permutation, but it's not a permutation that we want. That means we doesn't include that in the number for this answer. Oh, you can have Tom and Jerry on the opposite end, and again that's not what we want. You want them to be adjacent, and so we cannot just say 130. Of course, you can do the manual counting. Every combinatorics problem can be solved using the manual counting. You can list if you can list all 120 ways you can permute, and then you count, okay, this works, this doesn't work, this what you want, this is not, and so on, and list them on, and just manually counting how many of them. That works. You're gonna get the answer eventually. But let's see if we can use something unique to help us solve this problem. So since we want Tom and Jerry to be adjacent to each other, then also we can think them like if we just bundle them together, maybe put a rope around them, tie them together or something, and consider them as one single person. Right? Or if it is harder to think about shares, then you reserve 2 shares and put them together as one single share, so that Tom and Jerry will sit on either of these chair, and then you have a share for A, for B, for C, for D. Right now, this becomes a problem of permuting 4 objects. Now it's 4 objects, so we have a share for A, for B, for C, and for Tom and Jerry. Right, so here we permute. We find the permutation of 4 objects. So the answer is, of course, it's 3, 4, 4. Or as we know, it's 4 factorial, which is 24. Right, so now we have 24 to arrange these objects. For example, we can have A, B, C, and then this pair, or A, the pair C, B, or a pair B, A, C, or B, A pair C, so on and so forth. So now we can list all 24 permutations of these 4 objects. And then we have to ask, are we done yet? Not yet, not quite, because we reserved 2 seats for Tom and Jerry, but we still have to put Tom and Jerry on those seats. And the number of ways we can put Tom and Jerry on those seats, after we arrange the seats, then the number of ways we can put Tom and Jerry on those seats is 2. Because there are 2 seats, so we can put either Tom, Jerry, or Jerry and Tom. It's only these 2 arrangements. Right, so now we have a rule of product. Oops, my bad. So now we tackle this problem into 2 steps. First, and now we have 2 steps, 2 arrangements to make. First, we permute the chairs, and we know there are 24 ways. Then for each permutation, we have to seat Tom and Jerry in those seats. And no matter what permutation it is, we have 2 ways to seat Tom and Jerry. There's 2 ways here, it's 2 ways here, it's 2 ways here, it's 2 ways here. Right, so that means we can use a rule of product. And now we get the answer should be 48. Oops, my bad. It's 48. Therefore, the answer to this question is 48. There are 48 ways to seat Tom and Jerry together, to permute these 5 people such that Tom and Jerry are next to each other. So that's one example. You can see that there's no definite answer on the choose. But if you have seen this kind of problems enough, then you know what to do first, second, third, and so on. And then let's take a look at a short example 2. Now we are asking for the same question, but Tom and Jerry are not adjacent to each other. Right, so now they hate each other or something. I don't know. So that means if you have A, B, C, T, and J as before, now we don't consider that, right, because they are next to each other and they might bite or something. So that means we're gonna have to put at least one person between those 2. So that work. So we can have Tom, C, Jerry, A, B. That works too, because there is at least one person in between. So let's see if we can count them all. Then we have of course we have the manual counting, which is not recommended. Count them all. We have a second way. So we're gonna have third way. The third way is gonna be the best way, but let's see the second way. So we once we read this question, you might have to think about how can we arrange Tom and Jerry so that they are not adjacent to each other. And so if they are not adjacent, that means there must be at least one person between them. So that means out of all configurations, then there will be some that Tom and Jerry are separated by exactly one other person. Maybe it's A, B, and C. And that's going to be one of the possible configurations or permutations. Oh, there can be two people between them. Well, and then we gonna have to put the last person somewhere in the front or on the back. And lastly, we can have them. We can have all three people in case that they hate each other so much. We can do it this way. Put A, B, and C in between T and J. Right, so in this case, if you decide to use this approach, then what we are using here is what we call the rule of sum. Now we are using the rule of sum because we divide the problem into three separate cases, where each case are totally different. They have no common element. If there is one person in between, then this configuration or this permutation is not gonna appear in anywhere else. And so out of all eligible permutations, one we can partition or we can divide it into three cases. Right, so now we can use the rule of sum and then count each of these separately one at a time. Right, maybe this one is a to count. Let's try that. Right, so if you want Tom and Jerry to be on the ends and A, B, and C to be in the middle, then there are in this part for this part we need to use the rule of product. Right, so we have for Tom and Jerry there are two ways to put Tom and Jerry. Either Tom at the front, Jerry at the back, or Jerry at the front, Tom at the back. Then we have to put A, B, and C in between. Oh, yes, we have to put A, B, and C in between. And the number where is 3 factorial. Maybe we have 3 objects, we permute them all. So the answer is 6. Oh, sorry, 6 times 2 is 12. Okay, so the number of permutations here is 12. And once you finish that, then we have to, go through the other 2 and count them in the right way. I'm gonna stop here because we actually, you can do it, but we actually have a better way to count, which is to use what we have known already. So this is it's kind of the rule of sum in a way that we have all configurations, we have all permutations of 5 people. We know that for the each of them have the property that Tom and Jerry are next to each other. That means the rest of the permutations, Tom and Jerry are not adjacent. It's as simple as that. In set notation, we can take this. If you define that this to be the set A, then this is the A complement. It is a complement by definition. If it's not adjacent, then it is not adjacent. That kind of tautology. Right? And then since we know that the number of total permutations is 120, and this whole box, there are 120 permutations. That means the rest of the box, the missing part, for this question, the missing part is 120 minus 48, which is 72. And now we have the big answer. Right, so here you can see we can count in various ways, but sometimes we can count them in the right way. Or if you know something already, then we can use that knowledge to help us speed the process of computing. Oh, and by the way, if I just present you this is example 2, it means you have to complete this one first. But you have to count how many ways are there that Tom and Jerry are adjacent to each other, and then use that number, use that 48 to compute that. Right, so here that's another example that might help you see what kind of technique we can use Let's take a look at the third example. Now let's suppose the question asks how many ways to choose 10 people to form a group of 5 people, so that Jack and Rose are in the same group, whatever those people are. So there are 10 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there are 2 special people. They Jack and Rose. Right. Somehow we want to put them into a group. Now let's pause and think about what kind of problem is this about. This is the word choose. And when you think about group, when people are in the same group, we don't care if they are first, second, or third. Right? So in this case, this is a problem about combination. And you select those people without caring about the order of the sequence. So when you want to choose 5, let's use the previous notation where we put them in the back. Not like we kill them or something yet. Just think about them as an object. So we want to put them in the back such that Jack and Rose are in the same group. And so somewhere here there must be a Jack, somewhere here there's me a Rose. Then we count how many ways are there. Then we look at the back because we already have the back. Alright, let me zoom in a little bit. We already have the back. Since we are required or we are forced to put Jack and Rose in the back, then how many ways can we put Jack and Rose in the back? 1. Right, because we are forced to put them in the back. Unlike the previous problem where we have to permute them to see who is first or who is last or who is on the left or right. But here Jack and Rose are in the back, so we just put them. Then we use the rule of product to see how can we put the rest, and how we can fill the back, fill in the back. And there are 1, 2, 3 spots saved. Right, we have 3 spots, and we have to choose from 10. No, right, that's 10 now. Now we have 8 people left. Out of these 8 people, we have to choose 3 to join the same group with Jack and Rose. That means the number of ways to choose to fill the rest of the back is 8 choose 3, C8 3. If we have 8, we choose 3 to fill in the rest of the back of the back. So the answer is 1 times that, which is just that. That's the answer, C8 3. 8 choose 3. Or if you want to compute for the exact number, it's a factorial divided by 3 factorial, and then the difference, x minus 3 factorial. And then it's x factorial over 3 factorial, 5 factorial. If you do the math, x factorial and 5 factorial are cancelled to give you x times 7 times 6. Because the rest is cancelled by 5 factorial. And then we have 3 times 2 times 1. And here we can cancel 6 and 3 times 2. And then we are left with 56. So the answer is 56. There are 56 ways to form this group with that requirement or with that restriction. Right? Okay, now we have one simple question. Let's move on to next. How can we deal with the problem where there are repetitions?